Have you ever looked up at the sky on a sunny day and wondered, what if I could just fall into the sun? It sounds like a wild idea, right? But it's a super fun thought experiment. Our sun is a very special kind of star called a G-type main sequence star, or a yellow dwarf. This might sound complicated, but it's actually pretty simple. Think of it like a cosmic category. G-type stars are the just right stars in many ways. They aren't the biggest or hottest stars in the universe, but they also aren't the smallest or coolest. They are stable, long-lasting balls of glowing gas, and they provide the perfect conditions for planets like ours to exist around them. So, what makes a star a G-type? It's all about its temperature and color. G-type stars have a surface temperature of about 5,200 to 6,000 degrees Celsius. That's 9,400 to 10,800 degrees Fahrenheit. This temperature gives them a beautiful yellowish-white glow. Our very own sun is the most famous G-type star we know, but there are billions of others just like it scattered throughout our Milky Way galaxy. Stars like Alpha Centauri A, which is one of our closest stellar neighbors, is also a G-type. Alright, let's put on our imaginary super advanced spacesuit and start our journey toward the sun. As we get closer, the first thing we'd notice is the light. The sun would grow from a bright dot into an overwhelmingly brilliant orb that fills our entire view. It would be brighter than anything you could ever imagine, a pure, intense white light that would require the most powerful sunglasses ever invented. We'd see the sun not as a smooth, perfect ball, but as a churning, dynamic surface. There would be dark patches called sunspots, which are actually cooler areas on the sun's surface. Even these cool spots are thousands of degrees hotter than any volcano on Earth. As we zoom closer, we'd start to feel the heat even through our magical spacesuit. The temperature and space around the sun would climb incredibly fast. We'd also start to feel a powerful force pulling us in. This is gravity. The sun is so massive, it contains over 99.8% of all the mass in our entire solar system, that its gravitational pull is immense. Before we even reach what we think of as the surface of the sun, we have to travel through its atmosphere, which is surprisingly complex and has a few mind-bending layers. The outermost layer is called the corona. The weirdest thing about the corona is that it's actually much hotter than the surface below. The surface is about 5,500 degrees Celsius, but the corona can reach temperatures of millions of degrees. Scientists are still trying to figure out why. Just below the super-hot corona is a layer called the chromosphere. The name means sphere of color. During a solar eclipse it appears as a reddish ring, but still incredibly hot, around 6,000 to 20,000 degrees Celsius, where we'd see giant jets of hot gas called spicules shooting up like fiery grass. As we continue our fall, we finally reach the layer we can actually see from Earth, the photosphere. This is what we consider the sun's surface. The photosphere is covered in a pattern of bright cells called granules. Each granule is about the size of Texas. So, what happens when we finally cross the photosphere and fall into the sun? Well, the journey from here on out would be very fast. The moment we pass through the photosphere, our journey is essentially over. The combination of unbelievable heat and crushing pressure would vaporize our imaginary spaceship and its passenger in less than a second. As we plunge deeper, we would be traveling through the convection zone. It's kind of like a giant boiling pot of soup. Hot plasma, the superheated gas the sun is made of, rises from deeper inside, cools as it reaches the photosphere, and then sinks back down again in a continuous, rolling motion. We would be tossed around in these massive, country-sized currents of plasma. If we could fall even deeper, we would pass from the convection zone into the radiative zone. A single photon, a particle of light, created in the sun's core, can take over 100,000 years to travel through the radiative zone. Finally, at the very center of it all, is the core. This is the sun's engine room. But it is incredibly dense and hot, with temperatures soaring to 15 million degrees Celsius, 27 million degrees Fahrenheit. The pressure here is 265 billion times that of Earth's atmosphere. It is in this tiny, super-pressurized furnace that nuclear fusion happens. In our final moment, we would become part of this stellar engine, our atoms joining the cosmic dance of fusion at the heart of a star. This wild journey into the sun might just be a thought experiment, but, studying G-type stars like our sun is one of the most important things we do in science. By understanding our own star, we learn about the engine that drives life on Earth. Studying the sun helps us predict space weather, like solar flares and coronal mass ejections. Our satellites power grids communication systems here on Earth. Studying the sun also gives us a window into the lives of other stars throughout the universe. Since our sun is a fairly typical G-type star, what we learn about its life cycle, its birth to its eventual expansion into a red giant, helps us understand the billions of other stars like it. Furthermore, the quest to find life elsewhere in the universe is deeply connected to the study of G-type stars. Since life on Earth evolved around a G-type star, scientists believe that similar stars might be the best places to look for other habitable planets. When astronomers use powerful telescopes to search for exoplanets in the habitable zone, the area where liquid water could exist, a simple ball of glowing gas 93 million miles away holds the answers to some of the biggest questions we can ask, reminding us that there is always something new and amazing to discover.